Welcome to EDU World Space.
So in this video, we're going to go over question 82 from chapter 20, which says the resistivity, a measure of electrical resistance of graphite, is 0.4 to 5.0 times 10 to the negative 4 ohm centimeters in the basal plane. The basal plane is the plane of the six-membered rings of the carbon atoms. The resistivity is 0.2 to 1 ohm centimeters along the axis perpendicular to the plane. The resistivity of diamond is 10 to the 14th to 10 to the 16th ohm centimeters and is independent of direction. How can you account for this behavior in terms of the structure of diamond? So basically, we're told that graphite has the lowest resistance, meaning it's the best conductor in the basal plane, and then it's a slightly worse conductor in the axis perpendicular to the basal plane, and then diamond is an even poorer conductor, has an even higher resistivity. So let's go over what the structures of diamond and graphite are, and we'll talk about how those can account for these resistivities. So the structure of diamond is this tetrahedral lattice, where each carbon is the center of a tetrahedron, and each carbon is bonded to 4 other carbon atoms. So you have this tetrahedral lattice in which all of our valence electrons of our carbon atoms are tied up in these bonds, and these bonds making up the lattice. So all of our electrons are already occupied. So it might make sense that diamond would have a high resistivity and be a poor conductor because it doesn't have any valence electrons to travel throughout the lattice because they're all tied up in the bonds. Graphite, on the other hand, is not a 3D lattice. It's a two-dimensional hexagonal lattice. So you have these interlocking six-membered rings making up a two-dimensional lattice, and then in the third dimension, they're stacked like layers. So in this case, each carbon atom is not bonded to 4 other carbon atoms. It's only bonded to 3 other carbon atoms. So you have, so not all of carbon's valence electrons are tied up in bonding. So you have delocalized electrons in these rings. But you can imagine how it would be easier for these delocalized electrons to travel kind of between rings in the basal plane than it would be for them to travel between layers perpendicular to the basal plane. So because of this two-dimensional hexagonal lattice where your layers are not covalently bonded to each other, they're just connected by intermolecular forces. You can see how that would cause poorer conductivity and a higher resistivity in the direction perpendicular to the basal plane, whereas the basal plane allows conductive electrons to travel throughout the plane from ring to ring because you have your carbon atoms only bonded to 3 other carbon atoms, allowing for those delocalized electrons.